Welcome to a lesson with Dr. Powell. Let's take a look at finding implicitly a partial, maybe partial z with respect to x. And suppose that we have a relationship like this, z squared x plus z y plus x. Okay, and we want to figure out, and maybe that's equal to 4. Now, let's not solve for z. There's other ways of doing this. Let's think of this as being a function with 3 different inputs. And ultimately, let's think about taking the derivative of this with respect to x, okay, with the change of x. And in doing so, let's think about x and y as being independent of each other. So if one changes, then the other one doesn't change. And let's think about z as depending on x and y. So z actually depends on thing, okay, depends here. So let's think about this. This is a level surface, set equal to 4, this becomes a level surface of that function with 3 different inputs. So if we were to compute partial f, partial x, and we want to compute partial f and partial x, but we want to do so in a particular way. Okay, so first we're going to use the chain rule here. We take the derivative of f first with inputs x, y, z, so we're going to have 3 different columns. So we're going to get z squared, we're going to get z, and let's see, we get z squared plus 1. Okay, remember that one. And then we have for y, we get z, and then for z, we end up getting 2zx. Maybe put columns here just so I know what it is. 2zx plus y. Okay, derivatives of this is y, 2zx, and z, and then z plus 1. Right. Okay. So that's the derivative. Now, if we think about plugging this into, we're going to think about this as just being a function of x. So only thinking about one input. So one input, and think about x, y, z as being our outputs. So for our derivative, we're going to have something like this with 3 columns for the 3 outputs and 3 rows, sorry, 3 rows for the 3 outputs and 1 column for the 1 input x. And we think like this: partial x, we're taking derivative with respect to x everywhere. And this guy, since y and z are independent of each other, a little change of x induces no change in y. So this ratio, this derivative, is just simply 0. You can imagine here, a certain run of x will be the same. The ratio to rise of x is, that's the same thing. It's just one ratio is 1. And look, right here is actually what we want to find out. Now, if we stay on this surface and we want z to change in a way such that we remain on the surface, if x changes, then we want the rise of the function f with the change of x to be set equal to 0. If we were to plug something in. So this right here is the derivative. It's not really the rise. However, if you use a dot product, you get a number. So the derivative is just a single 1-by-1 matrix. And so the input would actually be a 1-by-1 as well for a rise. And so it's just a number. And so if you put a rise, which is like a change of x or something, and you multiply it to it, you want to be able to just get 0, because you don't want f to change from the level surface of 4. So f staying constant keeps us on the surface because it's a level surface here of the function. So this is what we want. When we multiply by any run here, we want to get out 0 rise for our function. Okay, well, that'll require that this whole bit be 0 itself. So we can actually use that. So as a derivative number, we want that to be equal to 0. Okay, so in taking this dot product, we come up with a relationship where we can actually solve for partial z, partial x. So let's go for it. When we do that, we get z squared plus 1 plus 2zx plus y times partial z partial x, and that's equal to 0. Solving for partial z partial x, we end up getting negative quantity z squared plus 1 all over 2zx plus y. We have just solved for partial z partial x. In particular, if x changes by a certain amount, this gives us the ratio for how much z will change. So let's just figure out what that would be right at the point 1, 1, 1, maybe. So we stick 1, 1, 1 in. See, well, at the top, we're going to get negative 2. On the bottom, we'd get a 3. So that means our ratio would be negative 2/3 at the point 1, 1. What does that mean? That means as x changes by a length of 1 unit, it means z would drop by about negative 2/3 right there at that point 1, 1 and moving just in the x direction. So kind of a neat piece of information for the surface at hand right here, thinking about the relationship between z and x. Even though we haven't actually solved for z at all, we can still get information about this implicitly. This is implicit differentiation, thinking about x and y being independent. Thanks for watching.